Welcome to the deep dive. Today we're getting right into, well, maybe the single biggest hurdle in managing global fisheries, not having enough data.
It really is the central problem. Something like 90% of fisheries worldwide, they just don't have the data needed for those traditional, really detailed stock assessments.
Which means management often relies on, well, guesswork, doesn't it?
It does, and that can lead straight to overfishing, sometimes even collapse. It's a huge issue.
Exactly. But we're looking at a paper today that tries to offer a way forward. It's titled A Novel Length-Based Empirical Estimation Method of Spawning Potential Ratio, SPR, and Tests of its Performance for Small-Scale Data-Poor Fisheries.
The lead author is Adrian Hordyk, and this is work from his team back in 2015.
And we're doing a deep dive into what they found.
Yeah, and their mission, it was pretty bold, really, but also kind of elegant. Can we figure out how healthy a fish stock is just by measuring the length of the fish caught? Nothing else.
Yeah, length. Okay, let's unpack the why first.
Yeah.
Why this focus on only length?
Yeah.
I mean, isn't aging fish the gold standard? Doesn't that give you the best data?
Oh, ideally, yes. Age data tells you so much about growth, mortality. But think about the practical side. For many fisheries, small ones, remote ones, a lot of tropical fisheries,
Yeah.
getting age data is just, it's a massive barrier. You need labs, skilled people to read otoliths, the ear bones, it costs a lot.
Right.
And on top of that, for many tropical fish, they just don't lay down clear annual rings like, say, a cod. So biologically, aging them is incredibly difficult, maybe even impossible sometimes.
Okay, so we often end up with piles of length data because anyone with a ruler can get that right.
Exactly, easy to collect.
But we need to turn that simple measurement into something managers can actually use.
We do. And probably the most useful single number for setting sustainable limits is something called the spawning potential ratio.
SPR.
SPR. Remind us what that actually means. So SPR is basically the fraction of the reproductive potential the stock has now under fishing pressure compared to what it would have if it were completely unfished.
Okay, so it's a ratio, like a percentage of the original spawning power left.
Precisely. A pristine stock is 100% SPR. If it's fished so hard there's basically no spawning left, you're at 0%. It's a really intuitive benchmark.
And that number feeds directly into management targets. We always hear about 40% SPR.
That's the magic number, often. If 40% refers to the fishing rate that leaves you with 40% SPR. It's widely seen as a pretty safe, risk-averse target for a lot of species. Leaves enough fish reproducing to keep the stock going while allowing a harvest.
But why 40%? I mean, if the data's shaky, wouldn't aiming higher, say 60%, be safer? Doesn't picking the target itself introduce risk?
Oh, absolutely it does. Choosing 40% is often, a balance between playing it safe biologically and trying to get a decent yield. But the Hordyk model, the LBSPR method, it doesn't tell you what target to aim for.
Okay.
Its job is just to estimate what the SPR is right now as reliably as possible from length data. Knowing if you're at, say, 20% or maybe 50%, that's the crucial first step, whatever your final target might be.
Got it. That makes sense. Okay, now for the clever bit. How does this LBSPR model manage to use just length data and sort of replace all that complex age information?
Right. This is where the underlying theory, building on Hordyk's earlier work, comes in. The model basically assumes the stock is in equilibrium. So steady fishing, steady recruitment.
It's a stable situation.
Yeah, stable situation. And if that holds true, the shape of the length distribution in the catch is mainly driven by just two key life history ratios, dimensionless ratios.
The ratios rule, I've heard it called. What are they?
Okay, first is the ratio of natural mortality, M to the von Bertalanffy growth coefficient K. So MEP over K. What does that tell you?
It tells you about the pace of life, essentially.
Yeah.
If NIGAL is high, it means the fish tend to die off naturally pretty quickly compared to how fast they grow. So for a high McDollar species, even without fishing, you wouldn't expect to see loads of really huge ancient fish that just don't live that long.
Exactly right. Natural lifespan limits their maximum size. The second key ratio is fishing mortality, F, relative to natural mortality, M. So 5 Taylor.
That's the exploitation rate.
That's your fishing pressure, yeah. How much fishing is contributing to the overall death rate compared to natural causes?
Okay, so the model takes the species' inherent pace of life, our model, looks at the lengths you actually measured in the catch, and then it kind of works backwards. It asks, what level of fishing would have to be happening to this theoretical population to make its predicted length structure match my real-world data?
That's the essence of it. It uses a statistical method called maximum likelihood estimation to find the best fit.
Maximum likelihood. Sounds complicated. Can you give us the functional idea without the deep stat?
Think of it like this. The computer plays a sophisticated guessing game. It takes your length data, then it runs maybe thousands of what-if scenarios. It tries out different values for 5MLAs and also for how the fishing gear selects different sizes.
Right.
Maximum likelihood is just the process that finds the specific combination of those parameters, the 5MLA, the selectivity that makes the model's predicted length distribution look statistically most like the lengths you actually measured.
So it finds the best match.
It finds the best match. And once it's found that best fitting 5MLRs, it can calculate the corresponding SPR.
That's much clearer. Thanks. But even for this length-only approach, you still need some biological inputs, right? Things the model can't figure out on its own.
Absolutely. There are crucial pieces you have to provide. You need that Mankara ratio we talked about. You need data on maturity. At what size do these fish become reproductive?
Right.
And critically, you need two things about size. First, the asymptotic length. That's the average maximum size the fish theoretically could reach if they lived forever. Yeah.
And second, you need a measure of how much individual variation there is around that average maximum size. That's the coefficient of variation of LeVO or CVO.
CVO to few. Why is that variability important if you already have the average max size LeV50?
Because fish aren't clones, right? Some grow a bit bigger than average, some a bit smaller.
Yeah.
If you ignore that CVL, Lindsay, the model assumes every fish perfectly hits that single Leaville value.
Ah, okay.
That makes the predicted length distribution unrealistically narrow, and it can really mess up the FVL estimate. You need that CV to capture the natural spread of sizes you see in the wild.
Makes sense. Okay, so armed with those inputs, Inglemelan 50, Lehman 50, and CVL, the researchers put LBSPR to the test. They simulated different fish populations, right?
They did. 4 simulated species covering a really wide range of life histories, different weight-D ratios, from fast-living to slow-growing types.
And how well did the model do when it had the correct inputs? The results were initially very positive. When they fed the model the true biological parameters for these simulated fish, it consistently gave back accurate estimates of both 5MME and, importantly, SPR across all those different life history types.
So if you know your inputs correctly, the tool itself works really well.
It seemed to, yes, under those ideal conditions.
Did it work okay, whether the simulated stock was lightly fished or really heavily fished?
Yes, that was another key finding. Its accuracy held up across a huge range of exploitation rates, from an FML near 0, like 0.01, all the way up to a very high 5MA of 5.
That's important because you need a tool that works for stocks that are already in trouble, not just pristine ones.
Exactly. A tool only useful for unfished stocks isn't much help for management. This one seemed robust across that whole spectrum.
Okay, that's great news on the accuracy front. What about efficiency? Since collecting data is the bottleneck, how many fish did they find you actually need to measure?
Yeah, this was a really practical insight. They found that while more data always makes your estimate statistically more precise, tighter error bars, the actual estimate of SPR itself was pretty stable and well estimated once you got to about 1,000 measured individuals.
1,000 fish. That feels achievable for a small local team or a cooperative.
It really does. It suggests you don't necessarily need to measure tens of thousands every single time. Hitting that 1,000 sample mark might be enough to capture the main features of the length distribution needed for the model.
Making the whole approach much more feasible on a limited budget.
Precisely. That's a key part of its appeal.
Okay, but models always have assumptions, and simplifications often come with weak points. Let's talk about the sensitivities. Where does this LBSPR model start to look a bit fragile?
Right. This is crucial. The sensitivity tests really highlight the model's, its Achilles heel. It's extremely dependent on getting those input parameters right.
And which one was the most critical?
By far, the most sensitive input was the assumed asymptotic length, 11 and 50.
The maximum size, okay, how bad is it if you get nullity wrong?
It can be. Pretty catastrophic, actually. The paper showed that if you specified LeVO just 25% higher than the true value...
Just 25%.
Yeah. For some life history types, particularly those with low malafide ratios, that error could cause the model to overestimate the fishing mortality, 5ML, by as much as 400%.
400%? Wow. So you could think a stock is massively overfished when it actually isn't, just because your guess of maximum size was a bit too high.
Exactly. It leads to potentially huge management errors. And the flip side is true, too. If you underestimate LeVO, the model might see only small fish and conclude there's hardly any fishing happening at all because it thinks they just can't grow any bigger naturally.
So the take-home is, the model run is cheap, but getting that LeVO input right, That requires real care. You can't just guess wildly.
You really can't. It underscores the need for good background biological knowledge.
Okay, what other assumptions cause problems?
Mm-hmm.
You mentioned the equilibrium assumption earlier, constant fishing, constant recruitment. Real life isn't always like that, is it?
No, definitely not. Recruitment, the number of young fish coming into the fishery each year, can swing wildly. And this was the second major area where the model showed limitations.
How did it cope with recruitment variation?
It struggled, especially when the variation was really high, say when the strongest year classes were 10 times bigger, or even more than the weakest ones.
Right, big boom and bust cycles.
Yeah, and it performed particularly poorly when those strong and weak years tended to clump together what we call autocorrelated recruitment.
So several good years in a row, then several bad years.
Exactly. That really throws off the equilibrium assumption. In those cases, the model didn't fit the length data very well, and the SPR estimates could be way off errors up to 100% in fab dollars.
So again, potentially telling you the stock is twice as exploited or half as exploited as it really is. Is there a warning sign for managers using this? Like, if the data looks a certain way, should they be suspicious?
Yes, the paper points this out clearly. If your measured length data looks highly multimodal, meaning the graph of lengths has several distinct peaks or bumps, that's often a sign of really uneven year class strength messing things up. If you see that pattern, it's a strong indicator that the LBSPR model's core assumption is violated, and you should be very cautious about trusting the SPR number it spits out.
Okay, lefty sensitivity, recruitment variability. Was there a third main issue?
Yes, and it relates to the fishing gear itself, specifically something called dome-shaped selectivity.
Dome-shaped selectivity. What's that?
Well, the basic LBSPR model assumes that as fish get bigger, they become more and more likely to be caught by the gear up to a maximum size, and then that high catch probability stays high. That's asymptotic selectivity.
Okay, bigger fish are easier to catch. Makes sense for some gear.
Right, but some gear, like maybe certain gill nets or even some trawls, they might be really good at catching medium-sized fish, but they're really big old ones. Maybe they can avoid the net or even swim right through the mesh.
Ah, so the gear selects against the very largest fish. Like a dome shape on a graph catches middle sizes best, less for small, less for very large.
Exactly. And when that happens, the catch data shows fewer big fish than you'd expect based on the biology alone.
And the model, not knowing about this gear effect, what does it conclude?
It makes the wrong inference. It sees the lack of those really big fish and assumes it must be because fishing pressure is incredibly high that fishing has removed them all.
Instead of them just avoiding the net.
Right. So with dome-shaped selectivity, the LBSPR model will tend to overestimate millers and consequently underestimate the SPR. It paints a bleaker picture of the stock status than is actually true.
So another crucial piece of information needed before you run the model. You have to understand how your fishing gear actually works across different sizes.
You really do. It's not quite a plug-and-play tool despite its simplicity. Knowledge of layabie and gear selectivity is paramount.
Okay, so they did all these simulations. Did they try it on a real fishery too?
They did an initial empirical test, yes. They applied it to data for female yellowfin whiting in Shark Bay, Western Australia. And they had results from a traditional, more complex, age-based assessment for comparison.
And how did the LBSPR estimate compare?
The traditional age-based method suggested the stock was in pretty good shape, an SPR of about 0.62.
62%.
The LBSPR model, using just the length data, came out with a lower estimate, SPR 0.44.
44%. So, more conservative, suggesting the stock was more heavily fished than the age-based method indicated.
Exactly, which in a way is potentially useful a precautionary estimate.
True. But did they also test how sensitive that real-world result was to the input assumptions?
They did, and this really drives the point home. Just by tweaking the input values for Seveldi and FDS within plausible ranges for that whiting stock, the resulting SPR estimates from the LBSPR model swung wildly. They got estimates ranging from as low as 0.18, indicating severe overfishing, all the way up to 1 down, which means pristine, unfished.
Wow. All from the same length data? Just by changing the biological inputs?
All from the same length data. It just hammers home how absolutely critical getting those inputs right is.
Which brings us back to the original problem, doesn't it? If the whole point is to avoid the cost and difficulty of age data, how do you get reliable inputs like Levante and Mesgol without doing that very work you're trying to avoid?
Yeah, that's the paradox. And the paper suggests the way forward isn't necessarily direct measurement for every single stock. It's about being clever, using what we already know.
How so?
The recommendation is to lean heavily on meta-analysis, looking at data from many other similar, well-studied species, and on life history theory.
Using established patterns, like how different traits relate to each other across species?
Exactly. For example, there are known relationships between, say, mem-call dollars and the ratio of maturity size to asymptotic size. So you might not need to measure number dollar directly for your specific stock.
You could estimate them based on these broader biological rules and data from related species?
Precisely. It's a way to get plausible, reasonably accurate input parameters cost-effectively, leveraging existing global knowledge.
So applying LBSPR isn't just about getting an assessment number. It can also act like a diagnostic.
Yeah.
If your results bounce all over the place depending on HLFT, the model is basically telling you.
It's shouting, hey, your biggest uncertainty here is the growth curve. Focus your limited research budget on nailing down a Lilling 50 better.
Right. It helps prioritize future research where it's most needed. It gives you a starting point, even if imperfect, where maybe there was nothing before.
Exactly. It provides that first step on the assessment ladder.
Okay, which leads us towards a final thought. Given how sensitive LBSPR is to things like recruitment variation, those non-equilibrium conditions, should we really be putting all our faith in a single snapshot assessment from any method in a given year?
That's a great point, and the paper touches on this. Trying to get hyper-accurate precision from one assessment in one year, especially when the system is naturally fluctuating, it might be the wrong goal.
So what's the alternative?
The paper suggests, and subsequent work has built on this, that the real value might lie in using models like LBSPR within iterative harvest control rules.
Unique.
Meaning, you move away from reacting sharply to every single year's assessment number. Instead, you use the model results over several years to guide a longer-term strategy.
Like course correction over time.
Exactly. You set a harvest rule designed to gently push the stock towards your target SPR over, say, 5 or 10 years, smoothing out the year-to-year bumps. It's about managing the trend, not micromanaging the annual fluctuations based on potentially noisy data.
So the final provocative thought might be this. If these simpler models, like LBSPR, are so incredibly sensitive to getting fundamental inputs like lead empty rate, 400% error sensitive.
Yeah.
Can we responsibly roll these out across thousands of data port fisheries globally without first making that minimal investment needed to actually pin down those crucial life history parameters like maximum size and growth with reasonable accuracy? Isn't getting that foundation right the prerequisite for using the shortcut?
Yeah. That really is the critical question, isn't it? It's the difference between just hoping a simple tool works and building a robust strategy based on it, a vital distinction.
Thanking the listeners to this episode.